In some ways, I think my title is a result of somewhat of timidity. We had chosen the topic, or the title for this conference to be teleology and physics and biology, and I was a little worried about forcing myself into speaking explicitly about teleology and physics. So when I first came up with the title, I talked primarily about chance and order. So you can tell me later whether you think you find teleology in it or not. In 12 years of, and part of the reason I have my hesitance perhaps, 12 years of formal studies in physics, I cannot recall ever having encountered the word telos or teleology. Goals and intention were primarily restricted to experimental practice or career advice. There was the occasional loose talk about a massive object wanting to fall, electrons wanting to move against a potential difference, but everyone understood that was just anthropomorphizing, shorthand for was attracted by, or was repelled by, or was subject to a force in a particular direction. Final causes or goals as intentions were simply that for the sake of which played little or no role in my formation as a physicist, or at least so it seems. If there were any sort of philosophical musings in the physics classroom, they tended to center around questions about order and randomness. You begin your physics career constantly seeking right answers and making very precise mathematical predictions. Now, you know that you cannot reproduce these exactly in the lab, especially the freshman physics lab, but trusting that there is a right answer for a perfect order. That exactness is weakened as you learn more complex dynamics and complex problems, and eventually gets thrown out the window completely when you finally grapple with the quantum mechanical world. That desire to know the right answer, to see the order in nature, is seemingly thwarted by randomness. First, due to imprecise tools, but eventually, in an even more fundamental way, by nature itself. Through all of this, though, there is a weird growing comfort with the fact of uncertainty in the physical world and randomness, particularly as you begin to see the order that can come out of this chaos. Now, classical physics was built in some ways, and there's philosophic and physics reasons to argue for this, that about a presupposition, a hope, a promise of exactitude, that for every question we might ask nature, there was, at least in principle, the possibility of a definite answer. In practice, the complication of actual systems means that such exactitude was always limited by how well the initial conditions could be ascertained, but the laws themselves provided no barrier here. Now, of course, plenty of classical systems are, in practice, random and unpredictable in their details, most especially in systems with lots of parts, each moving really excitedly. You think about the individual molecules in a cloud of gas, or just about anything in an earthquake. So I'm going to try here to share a video very briefly. This is explicitly stolen from Stephen Barr, who I believe was watching earlier, maybe he's still watching, a video version of one of my favorite examples from his book, Ancient Physics, Modern Faith. Just give me one moment. There we go. And there. So if I placed a bunch of random items in a box, such as this one, and shake it around, the motion is unpredictable and chaotic. As the box settles down, the motion is no longer chaotic. Things stop moving, but kind of where they end up is random and weird and disorganized. They simply settle down in a kind of haphazard way. Yes, they're at the bottom of the box, but what's on top of what? There's no order there. If instead we shake up a box of ping pong balls, we carry out the same exercise. The motion is still just chaotic and random in certain ways, perhaps even more depending on how well the ping pong balls are bouncing. But as it slows, we don't end up with random and haphazardness. We end up with a very particular pattern. In this case, right, it's, you can see, let's see here. There we go. For each row, you get this sort of hexagonal pattern. Like there's these 7 ping pong balls that form a hexagon, and 7 ping pong balls here that form a hexagon, and 7 here and 7 here. That when they line up together next to each other, you get this hexagonal packing pattern, as it's called. In 3 dimensions, it gets even more complicated. The result is this random motion. Is this 6-fold symmetry in some way. If I took any one of those sets and rotated them, there would be 6 different angles I could rotate them through. Now, this hexagonal pattern actually shows up all over the place in nature. I mean, anytime you're trying to cram a bunch of roughly spherical or circular things together. So on the left, there's honeycomb, which are formed by the circular bodies of the bees themselves. On the right, it's a really close-up view of the eye of a fly, where you see these hexagonal packing of things. From one perspective, it seems like we got order completely out of randomness. There was no symmetry. We ended up with this six-fold symmetry. But from another perspective, we actually lost some symmetry. Look at each of these ping pong balls, right? They are, each one is ignoring the labels. They're spherically symmetric. I could rotate them in any axis by any amount, and they would still look roughly the same. So in fact, the ping pong balls themselves have an infinite symmetry, any angle. And yet once they're packed together, there's only a six-fold symmetry. So there's a way in which we actually lost some symmetry here. There's also a certain symmetry between each of the ping pong balls themselves. If I had painted each ball to be identifiable, then when the packing was done, it would still have the same hexagonal shape, but I could say, oh, the red ball is on top of the blue ball, which is on top of the yellow ball. If I shook it up again, I could see they might be in a different order, and I could distinguish one particular hexagonal packing from another. The fact that these are all roughly the same color, they're a little used, so some of them have more use than others. It's nearly indistinguishable each time I shake it up. This sort of symmetry and order arising out of randomness shows up all the time in physics. In some ways, it's the examples that Father Pinsent was pointing to are aspects of this, a certain order and symmetry that comes out of random patterns. And from a certain light, people think that already there's something of teleology, but I want to press on this a little bit more. Now, if we think about experiments, though, on individual electrons, protons, quarks, or photons, we've learned that these individual particles are notoriously hard to restrict and pin down and put in a box like the ping pong balls. In fact, the more we try to squeeze a beam of light, the more it wants to spread out. This is a diffraction pattern where a laser is shown through a very small hole, and you end up with a much larger pattern at the end. And yet, when the collection of particles, these electrons and protons and neutrons, settle down, they form a very definite arrangement and structure, the very elements of the periodic table. If we focus on the smallest of these arrangements, the hydrogen atom, the bound state of a proton and an electron, there are a whole host of particular ways that an electron might be bound to a proton for a moment, and they're oddly discrete. There is a discrete ordering of these electron orbitals. They're quantized into these very specific discrete sets of states, distinguished by their energy and their angular momentum. And you can see the sort of complex and somewhat beautiful pattern of where these electrons tend to reside. It's not that the electrons are actually spherical or actually donut shaped. The electrons are hanging out in these particular regions, broadly speaking. And while the electron theoretically an individual electron could theoretically be in any one of these discrete but nearly infinite collection of states, you could kind of keep going up this chain to a certain extent. It always, left to itself, settles down to the lowest energy state, the simplest ground state, losing the excess energy and momentum by emitting photons. But not just any photons, only those photons that correspond to the discrete steps between energy states. These rings here just kind of correspond, roughly speaking, to the different energy orbitals. And the only photons that can be emitted as an electron, if it perhaps starts out here in the sixth orbital, as it makes its way down to the first orbital, it has to make discrete steps. It might jump all the way, but it needs to make various steps. And so when we look at the light that actually comes out of an excited hydrogen atom, we don't get a smooth, continuous, random pattern of any sort of photons. We get a very specific spectrum of specific wavelengths or specific energies and frequencies of light. Conversely, when light is shown on hydrogen, so when we're firing photons at the hydrogen atom, the electrons again only interact with light at certain energy frequencies. The light that will get it from, say, the ground state to the third orbital, or the ground state to the fifth orbital. We end up with an absorption pattern where most of the light is actually completely transparent to the ignores the hydrogen. The electrons in there in the hydrogen are completely transparent to it. So because this, so these types of pattern, again, are not unique to hydrogen, but they're present in all of the elements, but with slight variation. Each element has a particular discrete pattern of energy and momentum states that are available to the electron. And that particular set of states will determine what particular collection of jumps the electron can make, and what sort of photons the electron can either, the electrons in that particular atom can absorb or emit. These patterns become even more complex when we start talking about molecules. When our atoms link together and share electrons, those nice sort of broadly symmetric orbitals start getting bent across towards other nuclei. And there is this for each as a more complex arrangement of molecules build up, the particular spatial arrangement of the nuclei is fixed by the particular pattern of electron orbitals around them, and the particular shape and structure of the stable electron orbits is influenced by where those nuclei end up. It's this complicated sort of dance of settling down in a certain way into the particular state of minimum energy that is unique for each particular type of molecule. And each unique arrangement will have, among lots of other interesting properties, all of chemistry, unique spectroscopic signature for what energies of light that electron will interact with. Some of these are still the energy required to move electrons around. Some of them are the energy required to cause the nuclei in the molecule to move with respect to one another. And you get a much more complex collection of spectra. And these are, in fact, some of the primary tools that physicists and chemists have used over the centuries, particularly in the 20th century, to probe the structure of molecules. And the only tool, arguably, that astronomers have to probe the physical and chemical makeup of the heavens. In a certain sense, the entire beautiful picture that Dr. Oberg presented to us is built on these on this idea of spectroscopy, that different the molecules she's looking for, the organic chemicals, all the different atoms, what a star is made of, where the way we know the composition of what's out there is by the particular spectra that arrive, and the particular patterns of lines that are either present or missing in the light that arrives to us. So there's arrangements of quarks and gluons to make up a proton and a neutron, the arrangement of protons and neutrons that make up a nucleus, the arrangement of electrons that surround a given collection of nuclei are not fixed by some geometric symmetry like those ping pong balls were. There's no edge of the nucleus that sits against the edge of an electron, or an electron, there's not, an electron here, an electron there next to our nucleus. Rather, the pattern is fixed by the very nature of the various forces, the strong force, the weak force, and the electromagnetic force that are that are holding together all of these particles. And the discrete way that electrons, photons, quarks, and gluons interact through these forces. Now, contemporary physicists understand these interactions as arising not out of a geometric symmetry, but out of a, in a certain sense, much more complex, and in another sense, actually more simple kind of symmetry, a sort of fundamental symmetry in the way the pattern of these forces. While the indistinguishability of individual particles is still very important, it is no longer the shape of the pieces that constrain the shape of the collection. We don't even actually have a sense of what the shape or size of the electron might be. We know we haven't found the edge of it yet. So it's not shapes connecting to shapes, but there is symmetry in the very forces that link them together. Now, all of these phenomena I've described, and I could go on about the beauty of why it is that when you build, when you put collections of molecules together, why it is that all of these don't collapse in on one another, why it is that there are the various complexity of chemistry. And in a certain sense, you could continue down the path I started and start to peel away the layers of much of the beautiful order that Dr. Oberg described in her talk. But I want to head a slightly different direction. All of these phenomena I have described are built on a certain randomness and indeterminacy. There's order, but here random is tricky. We want to be careful because it can carry a little bit of baggage with it sometimes. In this context, what I mean is not that when I say it's random, it's not completely without order. In that sense, maybe indeterministic is slightly better. Rather, the idea is that it's not completely predictable, and more specifically, that even in principle, it would never be possible to completely predict everything that's going on in these atoms. As much as I know about the spectrum of hydrogen, where the electron can be with respect to the nuclei, I cannot know whether any particular photon, even the ones that have the right energy, will actually be absorbed by a particular hydrogen atom. Or if it is absorbed, exactly when the excited hydrogen atom will emit a new photon or several in decay. This lack of certainty bugs people. It really annoyed the first generation of physicists grappling with this new physics of quantum mechanics. Everything that first generation of physicists had learned pushed them to the confidence that physics should be able to answer, at least in principle, every question we might ask nature. That everything we observe should eventually be precisely predictable, or at least have a likely story about how it could possibly be precisely predictable. The confidence in a sort of physical determinism that once we know the structure of things now, the laws of physics will predict necessarily and exactly where things will be in the future was quite high and seemingly universal among physicists. And yet, within a generation or two of the discovery of quantum mechanics, physicists had, generally speaking, simply given up on determinism, the dream of precise predictability. Not because they gave up on order and explanation, but precisely because they were able to explain so much more. Richard Feynman, who is a genius physicist and a masterful explainer and teacher of physics, wrote a very beautiful little book, QED, which stands for Quantum Electrodynamics. I highly recommend it, in which he explains the theory for which he won the Nobel Prize. But he explains it for non-physicists and without cheating. He doesn't explain some easier theory that's not actually really correct. He really takes on his our best understanding of how light and matter interact. And at one point, after introducing the fact that we cannot predict whether an individual photon, an individual particle of light, will go through or be reflected off a piece of glass, he takes a bit of a tangent. He says, philosophers have said that if the same circumstances don't always produce the same results, predictions are impossible and science will collapse. Here is a circumstance. Identical photons are always coming down in the same direction to the same piece of glass. That produces different results. We cannot predict whether a given photon will arrive at point A or B. This is one side of the glass or the other. All we can predict is that out of 100 photons that come down, an average of about 4 will be reflected off the front of the glass, and the rest will move right through. Does this mean that physics, a science of great exactitude, has been reduced to calculating only the probability of an event and not predicting exactly what will happen? Yes, that's a retreat, but that's the way it is. Nature permits us only to calculate probabilities, and yet science has not collapsed. He goes on to explain various familiar phenomena, including the things that just that something about light that just have been taken for granted since Aristotle. And he pauses again to muse. So I've used these examples to show you how this theory of quantum electrodynamics, which looks at first like an absurd idea with no causality, no mechanism, and nothing real to it. If you read the book, which is very readable, it is startling the way he goes about trying to answer these questions. And yet he really is underlying that, our best understanding of how these phenomena work. And yet it seems like there's no causality, no mechanism, nothing real to it, and yet it produces effects that you are really familiar with. light bouncing off of a mirror at equal angles, light bending when it goes from air to water, light being focused by a lens, even the fact that light travels in straight lines most of the time. How is it that by giving up on exact prediction, we are able to explain more in physics and science more general? One possible explanation was that, in a certain sense, science was never really about prediction at all. For instance, the very first exact science, astronomy, which set off the scientific revolution and underlies the amazing and detailed cosmology Dr. Oberth described, no prediction. I think I can make this proper claim. Dr. Oberth can correct me. No prediction of an experiment in astronomy has ever been correct, because no experiment in astronomy has ever actually been run. By which I mean we have no tools by which to go and manipulate or rearrange or probe the stars directly. The galaxies, the interstellar medium, anything outside of our solar system. We've gotten a little bit beyond that, but not very far. Astronomy is an observational science by which we receive passively this light and think deeply and mathematically about first where the light comes from. And eventually, once we realize that there was these patterns in the light, we could build amazing tools for looking really, really carefully and closely at light. And here, not just visible light, but radio waves and X-rays and even gamma rays in certain contexts. We have built amazing tools for looking very closely at light, which have improved the detail and sophistication of that observation, particularly paying attention to those spectroscopic signatures. Now, some of these tools were developed by experimental methods here on Earth. We look at what hydrogen spectrum looks like on Earth, and we compare that to what's in the stars. We look at what the spectrum of various molecules here on Earth are, and we compare that to what we see in the protoplanetary disk. And we just observe and try to make sense out of what we observe. What is the pattern that must be out there in the matter to make light that looks like this? Even as profoundly an experimental science as particle physics is not primarily about predictions, if you think about it correctly. At least not predicting exactly what some particle will do or exactly when it will show up. Now, theoretical physicists have an amazing track record of predicting what types of particles we should find, but to find them, we have to try to set up favorable conditions and build a detector, generally bigger and bigger and more massive detectors as we go along. We set up our detector, we set up whatever the proper conditions, either waiting for a cosmic ray or building an accelerator to collide things, and then we wait and we hope. Well, physicists have had a theory of the Higgs boson since the 1960s and have had a lot of indirect confidence convincing them that just had to be there by at least the 80s or 90s. It took at least 3 different particle collider experiments. And the final one, the Large Hadron Collider, was the largest machine ever built by man. And still, it only actually produces a Higgs boson once for every about 5 billion proton collisions, give or take a few hundred million. Well, we can predict new patterns and order based off of old patterns we have seen before. Much of our science, if not all of it, is not so much about building a setup that will necessarily bring about exactly what we want right away. Okay, so I'm a good, 20 minutes into this talk, and I've said a lot of things about chance and randomness, but I said very little about teleology since that opening paragraph. Or have I? Teleology, for those who are not familiar with it, those who, like me, had never heard about it in their studies of physics or science, comes from the Greek telos, which means roughly the end. It's one of Aristotle's 4 causes. That's why people find it intriguing. And it's often referred to as the final cause, as an alternative to teleology. And his basic definition, Aristotle's basic definition, was that it was the end or that for the sake of which. Now, the easiest first example he gives is, we can ask, why is he walking about? Why is some person walking about? Well, he's walking about so he can be healthy. He wants to stay in good shape. There is teleology in human actions. There's a reason why. We have goals. We do things in order to achieve those goals. We can figure out those goals by asking that person, somebody else or ourselves, why am I doing this? Why is he doing this? Now, animals, we can't ask animals what they are doing, but at least generally, and generally speaking, they won't tell us if you try. But by watching them, we can discern certain desires and goals Why is that squirrel running up the tree? Ah, he's looking to get away from that dog. We can even see something of a that for the sake of which in plants. Not that there are conscious goals. There's not consciousness in plants per se, but there are certain goods or perfections that the limited activity of plants compared to animals and human beings do actually tend towards. A houseplant might grow towards the sunlight for the sake of getting more sun. A plant absorbs sunlight for the sake of storing energy in sugars for later use. Even an acorn is, in some sense, for the sake of growing into an oak tree. Most people, if they haven't immediately turned off when the word teleology came up, are on board so far. If nothing else, they would agree that these are the ways that Aristotle uses telos and teleology. Now, those who think that there actually is something to this teleology in the natural world in some sense are generally speaking fine with it in human actions. Yes, we have goals, we choose these goals, and might even be open to it in animals. And if they've come along that far, they're probably at least open to the possibility of a certain teleology in plants. But teleology in non-living things, that's the ranks thin out pretty quickly. And by here, I mean, there's a way in which, yes, we can step back and see order, but is there actual teleology, directedness in the way that directedness in the very way that inanimate things move and act? Some argue that even Aristotle didn't think there was real final causality in the inanimate world. This is a debated point. Very few people want to go the route of assigning intention or desire, or even simply like goods or perfections to a rock or an electron. Yes, we find beautiful patterns, but what's the teleology of that random stone? What's the teleology of an electron? What teleology could an electron have? So I want to try from here to argue for what sort of teleology an electron has. Now, to do that, I'm going to presume a few things. I'm not going to start completely from scratch. First, I'm going to presume kind of a standard line about quantum mechanics, that it is actually fundamentally indeterministic. Many people don't like this. There are lots of interesting theories about why it may still be deterministic, but I'm going to presume it's indeterministic. Secondly, and perhaps for some people contradictorily, I'm going to presume that despite this, it is possible to coherently talk about causes and activities of particular things, particularly a sort of agent causality, that broadly speaking, we can talk about things acting in a certain way. And I'm going to use that language fairly freely. Now, this might seem like an odd combination, but I draw confidence for this pairing from the work in particular of Charles de Koninck, from a Thomist from the 1930s, trying to convince his fellow Thomists that this was reasonable. The work of Elizabeth Anscombe, and a lot of recent work that's been done by philosophers of science who are broadly sympathetic to a sort of neo-Aristotelian or Thomistic form of at least efficient and formal causality. So I'm not going to presume final causality, but I'm going to presume that we can talk about other sorts of more obvious, but more common senses of causality. And third, I'm sort of going to presume that there's at least some proper sense of teleology in individual plants and their activities. And I point you to tomorrow's talks for a defense of that. So I'm going to try and see how far we can get by comparing a plant, say an oak tree, to an electron. Okay, one more clarification before we dive in. As with all of Aristotle's four causes, they are sometimes used to describe changes or activities, those things that we think about, the actual processes in nature. And they're sometimes used to describe things. So let's focus on the first, motions. One change or motion of an oak tree is that it absorbs light in the process of photosynthesis. If we think about that, we might say something along the lines of a plant or a leaf or the chlorophyll molecule, however you want to place it, absorbs light in order to store energy in sugar, a teleology. There's a whole lot more we could say about what the sugar's for, why that might be good for the plant, but we'll just stop there. We have a change, we have an end or telos of that change. Well, electrons also interact with light, the simplest form of which would just be what's called Thomson scattering, where a low energy photon collides with an electron and they head off in a new direction, but with the same kinetic energy. So the same speed the electron comes in at, it leaves with the same speed, just in a new direction. Is there teleology in that? The electron interacts with the photon in order to go in a different direction. Is that teleology? In a very weak sense, yes, I think it is. And I'm not alone in this. The point is not that there is some particular good about the electron moving in this direction rather than the other, but that the very stripped down core notion of teleology is simply a tending towards, even if that is just a tending in some particular direction. This phrase of stripped down teleology I'm borrowing from Paul Hoffman, where he argues, drawing on Aquinas, that such a notion would apply even to simple inertial motion at root, because the only way that we can actually identify an efficient cause or a source of change or motion is with the help of a final cause or an end. Aquinas says in his Principles of Nature, the end is not the cause of that which is the efficient cause, but rather is the cause of the fact that the efficient cause is an efficient cause. The final cause is not some mysterious second mover that's pushing around the actual causes. And it's not a thing, even in a certain sense. It's more a kind of explanatory factor, that thing that makes an efficient cause make sense. An aspect of this idea is reflected in certain contemporary philosophical arguments about what is often called dispositions. To summarize way too much, way too quickly, there's a sort of standard way to talk about dispositions, like the common examples are fragility or malleability or solubility. Salt dissolves in water. It's not always dissolving, but it has a disposition to dissolve. And these dispositions are classically described since Carnap in terms of manifestations and stimuli. When some stimulus condition is met, the salt is being placed in water, then a manifestation is exhibited. The salt, dissolves. Now, there's a whole range of literature on dispositions with various ideas about what dispositions actually are. Are they powers rooted in things? Are they some sort of disconnected powers? Are they not powers at all, but just interesting patterns we kind of notice sometimes? But there's a general consensus that dispositions simply don't make sense if you don't have a way of specifying the manifestation. What's the point of talking about solubility if there's never anything that dissolves? Even if an argument can and has been made that we might be able to make sense of dispositions without stimuli, we still need the manifestation to make sense, what actually happens. And there are even a few philosophers who have connected that to the idea of teleology, thinking that how a disposition should be thought about is as teleologically tending towards that manifestation, perhaps in a very simple sense. So I would argue that this is a parallel sort of claim to what Aquinas is making, that there's a real sense in which an efficient cause, the kind of causality that we're most familiar with, only makes sense because it has a final cause or teleology, that we see the result. We know when an electron has actually interacted with a photon or exercised a mutual attraction with a proton or its mutual repulsion with other electrons when we observe the fact that the electron's motion has changed. Okay, so let's set aside teleology in motions and focus on teleology in things. So turn again to our oak tree. A classic example of such a teleology is what I mentioned before. An acorn is for the sake of a mature oak tree. So the mature oak tree is the telos of this acorn. Now, this is not in any way a claim that there is some spooky thing that is this ghostly mature oak tree outside of the acorn that is somehow yanking on the acorn and pulling it apart until it becomes that oak tree. No, nor is it the obviously patently false claim that every single oak tree will actually every single acorn will actually become an oak tree. Just ask the squirrels. There are plenty of acorns that don't make it. It rather is the claim that an acorn, which is an organism with a particular structure and biological activities, what Thomists and students talk about as a form, when it is put in the proper conditions, will use those activities to change its structure and organization over time to become a mature oak tree. That full mature oak tree is the same organism, but with more complex structure and activity, with more perfection. once our acorn actually becomes a mature oak tree, it has, at least in some sense, achieved its end. It still has motions, it still has activities, but they're not so much about adding new structure and new complexity, getting bigger and larger. The full oak is the same, but those actions are more about preserving, roughly speaking, the structure and complexity it actually already has, and staving off destruction and eventual death. So, what about our electron? Well, it doesn't have structure per se. Remember, I said we don't even know where the edge of it is. But it does have certain definable properties. Every electron has the same charge, spin, mass, what's called a color charge, meaning it doesn't have any. And so there are certain properties that are common to every single electron. Those properties help determine not simply what an electron is, but how an electron will interact with photons and other particles. It has certain activities. The only thing those activities really can change about the electron is the momentum and the kinetic energy, where it's heading and how fast it's going there. If there were an activity that could change any of the other particles, if there are properties, if there was some activity that could change its charge or change its spin, we wouldn't have an electron anymore. It would be something else. In a loose sense, our electron starts out already like our mature oak tree, having all the properties and activities necessary to be a perfect electron. And any activities it undergoes are primarily about preserving those properties, or at least not destroying them, and staving off any interactions that might try to destroy it. The final cause or telos of the electron is the electron, just itself. Now, this seems silly in some sense, but there's something to it. In his, again, the De Principiis Naturae, Aquinas distinguishes between two kinds of ends. First, there is the end of generation, so which he says explicitly coincides with the form. So when we are done making a knife, say, we know that when the thing we're making has the form of a knife, or in the case of an electron, when an electron is generated in some way, we know that that's happened when we see that it has the form of an electron. Now, the second kind of end he talks about, second kind of teleology he's talking about, is the end of the generated thing, which in his case of a knife is cutting. It's what a knife does. It's what it's there to do. So by analogy, then, what an acorn does is grow into a mature oak tree. What an electron does isn't grow. It just moves around as an electron. It exercises the sorts of activities proper to an electron without changing or growing into some more perfect structure. Albert the Great spends way more time talking about the nitty-gritty details of inanimate nature, stuff below living things. Aquinas usually brings it up in the context perhaps of the elements or when there's some particular reason, but he doesn't have a whole lot to say on rocks and metals. But so if there were something really interesting to say about the final cause or the teleology of rocks or metals in Albert's mind, we should find it in his book on minerals. Yet in, roughly speaking, 200 pages that he has on stones and minerals, their efficient causes, their substantial forms, their powers, their characteristics, all the various minerals he knows about, all the various rocks he knows about, where they are made, how they act and react. There is exactly, as far as I could find, one sentence on the final cause of minerals. Having spent at least a chapter, if not more, on each of the material, formal, and efficient causes of stones in general, he says, but we need not look for a final cause, since in physical things, the formal cause is the final cause. Note, he does not say there is no final cause in minerals, but simply that once we find the formal cause, we've already found once we find the formal cause, we already have also found the final cause. The teleology of a diamond is just to be a diamond and do what diamonds do, which isn't a whole lot. The teleology of gold is to be gold, which means resisting anything that might not be gold anymore, as well as doing certain activities that are proper to gold, which in Albert the Great's mind was sometimes cooling things down, broadly speaking, that it inherits from the wateriness of it, melting under heat under certain conditions, or shearing man's heart, which we thought was a particular proper action to gold. So at this point, if you're still with me, you may be wondering, okay, so what? I've picked some fairly basic features of an electron. It moves around. It is an electron. And I've said, aha, I have found teleology. What exactly does this stripped down idea of teleology do for us? And also, whatever happened to that randomness and order stuff? If I'm honest, I've been cheating a little bit here. Everything I've been saying about the teleology of electrons, the interactions of electrons and photons, I could have said almost exactly the same thing about billiard balls. Now, I will say, I think I can coherently link what I have been describing to actual particle physics experiments with a few nuances, perhaps even, I hope, to Feynman standards, but with certain qualifications. First of which is that because of quantum mechanics, even if I could isolate a single photon and send it at a single electron, I have no idea what the electron will do, how it will act, if it will act at all, until I observe the very things that I have claimed are the final cause or teleology of the electron. It's only by actually finding the electron after the fact and observing its momentum and energy that I can say anything about what the electron may or may not have done in relation to the photon. It is through the end, the telos, that I have any hope of saying what the causes or powers actually did. For billiard balls, I mean, once I know the direction and speed they start out in, any decent billiard players, any decent physicist, or roughly maybe half the students taking a freshman physics exam can tell whether they will interact and what direction they will head in afterwards. So at the very least, there is a case to be made that because of randomness and indeterminacy in the quantum mechanics, the only way that we can identify what actually happened is by observing this stripped down core notion of teleology in inanimate things. Now, the even more important qualification, though, is that I've been playing kind of fast and loose by focusing on individual electrons. While there are amazing and really sophisticated and very useful tools that physicists have developed to create beams of electrons, real, electron guns, literally, and we can even figure out how to slow them down so we see the effect of one electron hitting a screen at a time. We made ion traps that allow us to isolate individual subatomic particles under very specific conditions, not hold them still completely, but kind of bind them in a certain spot. Despite all of these things, the vast majority of electrons in the universe are not isolated. They're part of some larger material structure, some solid, liquid, gas, or plasma. Most of the electrons we normally encounter are bound to a nucleus in an atom. Although the universe as a whole, in the universe as a whole, so the ones we're familiar with are atoms, but in the universe more broadly, it seems most of them are probably in some sort of plasma. Roughly, that means that a large fraction of the electrons, or maybe even all of them, are not actually bound to individual atoms, but there's still this sort of interspersed mixture of free electrons and ions, these nuclei without any electrons, that act independently in a certain way, but still form an overall neutral structure. Overall, there's the same number of free, negative, and positive charges. In these cases, it becomes impossible to talk about the activity or power of a single electron, even though we can recognize effects that must happen because some particular electron must have interacted with some particular photon or ion. There's no way to really identify what electron did what, and even more importantly, the particular pattern of possible interactions that some electron, any particular electron we might want to talk about, in really serious, what larger structure it's part of. A free electron in a plasma would often interact very differently than an electron bound to a proton in a hydrogen gas, even when dealing with the same energy of photons. That free electron has a pretty decent chance of interacting with any photon that comes by. We don't know for certain, but it could interact with any of them. Whereas, as we saw, the electron in the hydrogen atom will simply ignore a whole swath of photons, a large range of energies of photons. The photon doesn't have exactly the right energy to move it up to a new orbital, or maybe it's strong enough to knock it out completely. It doesn't interact with it at all. even in these larger structures, the randomness, and further, that absorption that we saw for hydrogen gas is different from those that are linked to hydrogen in molecular water, or even whether that water is in ice or in water or vapor. So even in these larger structures, the randomness and indeterminacy of the quantum mechanics still makes perfect prediction of future interactions impossible. We are restricted to simply observing the end results of our interactions, the final causes or the teleology of various possible interactions that particular structures can have. I'm going to try to jump ahead a little bit for the sake of time. So when we look at the stars, right, we can make credible and reliable claims about what the stars are made of, where they are, and how they are moving, simply because of the particular pattern that is, in some real sense, just built on this stripped down teleology of the photons that they gave off. What is their energy and what direction they headed in? Well, I'm making some kind of bold claims here. There's a further argument to be made, and it's been made in much more technical and interesting detail for slightly different scientific grounds by Robert Koons and a few others, that if we're going to find real proper substances in the animate world, it's not actually at the level of the electrons or the protons, but at the level of these collective chemical substances, solids, liquids, gases, plasmas. Now, there may be some weird cases and difficult cases. I mean, electron guns are kind of powerful and interesting. So, but most electrons seem to be, properly speaking, part of something larger. It's not to say that they don't exist or something, but that their existence only makes full sense as part of this larger chemical structure. That's something about the very difficulty of dealing with in the individuality of a subatomic particle in one of those structures that we see in quantum mechanics. It's a sort of sign that that it's actually its full reality is actually being part of this larger structure. It's a sign that we shouldn't treat them as or think of them as individual things exactly precise in a certain precise way. So if that holds, then the various details that I've been talking about the particular way that electrons and protons arrange themselves in a sample of hydrogen gas, to stick with that first example, those orbitals, the various spectra that come out of it, the fact that they excite that electron, but then they'll settle back down to the ground state. That would properly be not about the relationship between lots of different substances, but that would be internal structure within a single substance. That the electrons and protons would bear a certain kind of analogy to the cells or organs of a living being. And the particular way they tend to organize themselves and react dynamically to outside influences to return to that normal state would be analogous in some sense to that internal dynamics of a living being. Okay, so I'm going to go back to that nagging question. So what is this glorified relabeling of familiar, perhaps to physicists, well-trod patterns of physics do for us? Sure, okay, it'll make some convinced Aristotelians and Thomists, those of us wearing white habits, feel a lot better about ourselves. But why should anybody else care? Does it change the way we actually study the physical world? Perhaps not. I'm not yet so bold as to claim that we should go back through my old physics textbook and put teleology in the right places. But does it add something to the contentious debates that show up in philosophy of science about why exactly is science so successful? Why do we actually think we know things when we talk about sciences? And here I am much more helpful. Aristotle and Aquinas were convinced that the natural world was inherently contingent and mostly unpredictable. The fact that they were probably a bit too pessimistic about the regular patterns. And yet they were both also at the same time completely convinced that there could be a proper science of nature, that you could have absolute certain knowledge about things in the physical world. And they were convinced of it, at least in part, in a large part, because of teleology, even in this sort of stripped down sense. They did not believe that even the best knowledge of the material constitution, formal structure, and the possible combination of actions that are going on in something was enough to ensure a necessary connection to something in the future. Given what things are now, we didn't actually know what's going to happen in the future. We couldn't predict in detail. But they did believe that when we actually observe certain ends, we could argue back to what must have been. Given certain final states, we can know for certain things about what led to them. If you find an oak tree, at some point, there was an acorn. This sort of teleological reasoning from the end back to other causes did not always lead to necessary demonstrative knowledge. Sometimes it was just probable conjecture. But the sort of forward necessity, the sort of desire for prediction was for them out of impossible, outside of the heavens. So, so the fact that an existence of teleology in the physical world, so what I want, the thing I want to conclude with then is to say that if I in my better days, I find myself convinced that if we could think about things in the sort of causal reasoning that Aristotle and Aquinas found quite compelling, extracted from the details of their outdated cosmology, I think there's a real way in which we could help understand what has made science, generally speaking, so successful, and also distinguish more clearly the certain instincts of scientists. There are certain things that by now we just know, even if cutting edge research is correctly qualified by certain error bars and uncertainty. The fact that an acceptance of teleology would also make, in the physical world, would make other aspects of teleology more interesting, might open up to arguments about the existence of God, might open up to the beautiful panoply of what we saw in our previous talks. I'll just take that as a bonus. Thank you very much.
All right, thank you very much, Father Thomas, for this lecture and this philosophical reflection on teleology, both in physics and in biology, actually, which kind of anticipates our conference tomorrow, the second part of the conference.
I was stealing ahead a little bit.
Yeah, stealing from me as well. So we have 3 questions so far. So I hope we'll have time to ask and answer all 3 of them. So the first one is asked by Luca Settimano once again. So Luca, please, if you could ask your question.
Yes, thank you so much for the presentation. So yeah, I put in the chat different things because I engage very much with your topic. So I guess the first very quick is, Pilkington speak of God creating using this chaos, and it doesn't mean, I think, that he's acting as a secondary cause among other causes, but we want to give, like, that he can give an input of active information within the process, given that there is this indetermination that you mentioned, and then the second one very quickly is, when you say that the electron knows that is an electron, the substance of an electron, I'm thinking water molecule, the form of ice and the form of water liquid. You cannot decide if a molecule of water is ice or is liquid unless there are other molecules next to each other. So there must be something about the relation within more than one molecule. One molecule is not enough if water is solid or if water is liquid. I wonder what you think about that. Thank you.
So to the second part of your question, first, I would highly recommend looking up, I'm blanking on the name, the work of Robert Koons on, I believe the titles would have something like chemical substance in it. I mentioned it briefly in the talk. He takes a very hard look at contemporary the contemporary mathematics of kind of quantum chemistry and attempts to sort of bridge the gap between talking about a couple of water molecules to a collection of water molecules, a glass of water, and seeing, is there continuity there or is there something else? And he makes a pretty strong claim that is a sign that there is something about there's a certain mathematical disconnect, and that's a sign that we should think of the water molecule or the water molecules in the glass as properly part of a substance. In a very particular way. I think there's some subtlety and lots of debates you could have about that. But I find that sort of reasoning compelling, that we can poke at individual water molecules in a glass of water, and we can make them manifest themselves in certain ways. But we rarely have a water molecule and hold it in our hand and carry it around. There are edge cases where this gets very difficult. Most of the time, it's part of a larger mass and very hard to distinguish. In terms of the first question, I would say I intentionally did not bring God into the talk. I was trying to stay at a more philosophical level. I think there is absolutely a way in which God is working in every single one of these natural causes. Being a good Dominican, I believe in primary and secondary causality, that anything that happens in nature is also actually being kept in being and acted acted, being able to act because God is also acting. I'd have to look a little more closely at the details of what poking home. It's been a while since I've looked at that in terms of what he has to say about how God relates to randomness. I think there is randomness in nature. I'm convinced that the world is in some sense indeterministic. And I think first from Thomistic principles, even before quantum mechanics. But how God uses randomness is a thorny issue and not every, it can be hard to parse. So I hope that helps.
Okay, thank you. The second question comes from Jeffrey Bhullar from Toronto in Ontario, Canada. So Jeffrey, please ask your question.
Thanks very much for your talk. I enjoyed the oak tree and electron example. So
hopefully not too much of a stretch.
So I'm wondering, I was really affected by Julia Pearl's popular book on causality, causal inference. And he's using examples mainly for public health epidemiology, how to deconfound, how to control for this. But he really sort of abstracted another layer of math beyond Bayesian conditioning to when you intervene and you do things. Mm-hmm. So some quantum physicists have picked up on this causal inference and started to make the distinction between classical causality and quantum causality. Okay. And I'm wondering if you're familiar with that and what you think about, at some point our intuition for causality comes from a lot of, first person experience in classical world, classical measurement devices. And so at a certain point, are things going to be very different at a microscopic level because it's so outside of our experience? Does quantum causality have something to do with that?
So I'm not properly familiar with the details of the quantum causality that you described. I guess I can kind of give my as of this week current random thoughts on quantum mechanics and how it may or may not make sense. This is something I continue to think about and adjust slightly, but I do find compelling the idea that thinking, as in a kind of Thomistic mode, that the seat of being, the substantial form of things that exist most often are not individual electrons, individual quarks, individual protons. They are there, but they are not, properly speaking, things which have independent causality. What they do is they act as part of a larger structure. Now, the mathematics between the free electron and the electron in the hydrogen atom and the electron in the hydrogen atom in water, there's a smooth mathematical transition from one to the other. But if you step back and look at it, there's a very drastic difference between the way that an electron in a plasma interacts with a photon, an electron in a hydrogen gas, electron in water acts in a photon. There's the same powers of the electron in a certain sense are being manifested differently because each of those electrons is actually, properly speaking, part of something larger. It is the atom as a whole that is acting on the photon in some sense, not the electron individually. And so I think it has to do with finding the proper place in our hierarchy to think about where substances are, and the fact that we can talk about the material constitution of things and the parts of things, but that they may only actually fully make sense when we realize that they are parts of something bigger. So there may be an analogous way we can talk about maybe something like quantum causality. Again, I would need to look at the details, But properly speaking, the causality would be of the water that happens to be acting through this part at some times and that part at another.
Thank you.
Yeah.
Okay, so I believe we have time for one last question. There is more I have to choose now. Okay. And I think there's an interesting question coming from Hyung Yo Lee, who is a graduate student at the GTU in Berkeley. So Hyung, please ask your question.
All right, thank you. As I wrote here, it sounded to me that you were assuming a single endpoint when you talked about the final cause. But what if there are multiple endpoints? For example, we could imagine a multiverse scenario. And how would you explain the interaction between each endpoint and the present moment in that case?
So just to be clear, I understand what you're saying. When you say multiverse, are you talking about a many worlds interpretation of quantum mechanics, where in everything that we might talk about as an interaction or cause, we end up with branchings? Or are you talking about a multiverse in terms of, our universe coming out of the Big Bang is different from another universe with its own Big Bang?
I was talking about the latter.
Okay. And so then just ask your question one more time, just to make sure I'm on the right track here. Sorry.
Right. So, for example, if we have many different universes, then we would have a different shape of the. We would have different universes with different
different patterns and structure.
Yeah, and we would have a kind of theodicy problem as well, because there are many different futures which might seem not proper or not making sense at all.
Right.
So in that case, we have different endpoints, many different endpoints. But when you talk about a single endpoint which makes sense, then it will be very easy to explain why the present moment is like this, something like that. However, if we have many different universes which which do not make sense at all, then I think the explanation should be very different from the explanation you gave to us. So in that sense.
So I think, if I follow correctly, I think one kind of distinction that would be helpful to bring in here is that the particular kind, in a certain sense, I was taking as literally as possible the kind of topic of our, the title of our conference, teleology in physics, in the sense that I was looking for, okay, if we just look at things that aren't biological, do they have some sense of a telos, some sense of an ordering, some sense of, both in their activities and in their being? Is there some sense in which we can talk about an end? As you get up into large, as you look at, then I clarified the idea that, okay, perhaps we don't want to emphasize, say, the end of an electron as much as we want to talk about the end of the water as a whole, or the collection of hydrogen gas. Things get more complicated when you actually have different substances with different teloses that are then interacting and at times competing with one another. Sometimes not, sometimes working against one another. So, for instance, think of a star. You could think of a star as an individual substance, or I think you might be able to argue it as a collection of lots of different gases that are mixed together, lots of different plasmas that are mixed together. Each plasma, in a certain sense, has its own form and telos, but then there is a sort of collective activity, dynamic activity that comes out of the whole, that is the life of the star. And so I think perhaps if we're talking about, the telos of the universe as a whole, then we're actually looking at the mutual interaction of lots of different individual teloses of the actual substances that we find in nature. And that ends up leading to questions about how exactly, are there hierarchies in nature? When we find certain kinds of things that are bad for one substance, does it actually, in some context, make the entire universe better off? And Aquinas definitely has sort of things to say about that. And I think, arguably speaking, you might even be able to prioritize between different multiverses, where if there were lots of different multiverses, but only one perhaps where God became incarnate, there might be a priority to that one, such that even if we find one of these other multiverses is really weird and uninhabitable and seems not very good, its existence perhaps in some way makes reasonable or more possible the one where human beings came to exist and God became incarnate. So there's a way in which perhaps, as we move to the theological level, we can see God's perspective on the mutual interaction of both the telos of all of the different substances in any particular universe, and then the kind of collective perhaps telos if there were different multiverses. I hope that helps.